Hello friends, I hope you all are doing well. In this video we are going to learn how to design actually loaded short column for a real life example using this advanced Excel sheet. So by using this Excel sheet you will be able to design actually loaded short column. But before of getting into the calculation we will look at the problem statement. So here we have to design column C1 at the first floor level of G+1 RCC building, where the column is subjected to axial force of 820 kilonewton, and this force is actually service load. So here I am expecting that you all are well aware with service load and factored load. What does mean by the service load and what does mean by the factor load? I am not going to discuss these all things. But this column is connected by the beams in both the direction having the depth of 600 mm. So what is the application and what is the need of this data? Actually the depth of the beam, we will discuss it later. And the material to be used for the designing of this column as M20 and Fe500 for the concretes and rebars respectively. Here one more thing, in the figure you can observe that the height of the column C1 from ground to first floor level is actually 3 meter. So one more data we are having here, as the floor to floor height or total height of the column is 3 meter. Now coming back to our Excel sheet. So first of all I would like to introduce about this Excel sheet. So you have to edit the value only in yellow cells. You don't need to change the value in the white cells, because the white cell will adjust the value on itself because of the feeded formula in it. So always while using this Excel sheet, keep in mind you have to edit the values in yellow cells. Now without of wasting the time, we are going to start the calculation. So first of all we have to put the unfactored axial load. So as you all know that the 820 kilonewton force we have given as the axial force to the required column. Now next is we have to put the value for unsupported length of the column. So first of all it is important to understand what does mean by the unsupported length. So actually in the given example, what is given, see the total length is given here. The total length of the column is given here, but in our calculation we need to put the unsupported length of the column. So try to understand what is the difference between total length of the column and unsupported length of the column. Coming back, let's consider this simple representation of the structure where the slab is supported by the beams, at all the floors. So total length of the column means what? See, the top of the upper floor to the top of the lower floor, we are calling it as floor to floor height, and this is we are actually calling it as total length of the column. This is what total length of the column. But in the calculation we need to have unsupported length of the column. So how you can calculate the unsupported length of the column? So to calculate the unsupported length of the column, we have to subtract the value of depth of the beam. So in the given example, in the given statement of the problem, the depth of the beam is actually 600 mm in both the direction. So coming back, see total length is, length of the column is actually 3 meter, that will become 3000 mm, and depth of the beam is 600 mm. So unsupported length of the column will become this height, top of the floor to the bottom of the beam. So 3000 minus 600, this will give you finally unsupported length of the column, that will become 2400. In meter if you are calculating this value, so that will become 2.4 meter. So unsupported length of the column is what? 2.4 meter for our proposed example. Okay, coming back, just put this value as 2.4. Now the grade of concrete we have to use as M20 grade. So in this Excel sheet, drop down list is there. As per your requirement you can change the grade of concrete. Similarly, The grade of steels are also given here. If you just click here, drop down list will be there, and as per your requirement, as per your need, you can select the grade of the rebar. So for our proposed example, we have to use the grade of reinforcement as 500. Now restraint condition. Column is having two ends. Column is actually having two ends. One is top end and another one is the bottom end. So for this example, we are going to consider both ends as hinged. So different condition as per the IS 456 is there, as both end is fixed, both end is hinged, both one end is fixed, another end is hinged. So for this example, we are going to consider both ends as hinged. If you are changing the value, see, both end is fixed. Accordingly, your effective length factor is going to be changed. 0.65. If you are taking one fixed, one hinged, so accordingly effective length factor is going to be changed as 0.8. But in this example, we are going to consider both ends as hinged, so accordingly effective length factor will be 1. Now final effective length will be equal to effective length factor multiplied by unsupported length of the column. What? Just try to understand. Effective length of the column will equal to unsupported effective length factor multiplied by unsupported length of the column. That is what? 2.4. That will become 1 multiplied by 2.4. So sheet will give you this answer as 2.4. Now assume the percentage of the reinforcement. So I hope you all know very well what is the limit of the percentage of reinforcement in the column section as per the Indian standard. So that limit is from 0.8 to 6%. From 0.8 to 6%. If you look the IS 456 2000, so it is given here 0.8 to clause number 26.5.3 columns for the longitudinal reinforcement, it should be 0.8 to 6%. So accordingly here we have to assume the percentage of the reinforcement for the further calculation. Actually we have not designed the column just right now, but for the further action we need to consider this percentage of reinforcement. So in between of 0.8 and 6, I am going to consider 1.5% of reinforcement in this section. Now factored axial load, so that will be 1.5 times your service load or unfactored load 820. So if you take the multiplication of 1.5 with the 820, so you will get 1230 kilonewton. Now some self weight of the column we also have to add to this value. Self weight of the column I am going to consider as 1% of this value. 1% of this value, so that is going to be that becomes 12 kilonewton approximate. So total factor load that for which we have to design our column is 1242 kilonewton. Okay, now as per the IS 456 2000, the equation for designing of axial load column is Pu is equal to 0.4 FCK AC plus 0.67 Fy area of steel in concrete. This is the area of concrete. Okay, now first thing, what all the things are known here. Pu means axial force, factored axial force, we know. 0.4 we know, FCK we know, characteristic strength of concrete. Area of concrete is actually unknown. 0.67 is known, Fy is known, area of reinforcement is also known. So everything is known, only unknown is what? AC. So using this equation we can calculate how much area of concrete is required. So sheet will directly give you the how much area of concrete is required. So 95,378.12 mm square area of concrete is required. So as per the requirement of the concrete section, as per the requirement of the concrete area, we have to decide the section size. Now I am going to consider trial section size of the column as 230 by 300. So if I am taking the section size 230 by 300, so after the multiplication of 230 by 300, area provided will become 69,000 mm square. Requirement is what? 95,000. we are going to provide 69,000. So obviously provided area is less than required area. Obviously the criteria is failing. Your provided should always be more than the requirement. So here area required is 95,000 and you are going to provide only 69,000. So that is not okay. So this sheet will give the intimation that we need to revise the section size. So width is fixed, 230 is fixed. Now I am going to increase the section size as from 300 to 450. Just put it. So it is going to become 10,000, 1 lakh 3,500. That is more than 95,000. So area provided is more than area required. Now it's okay. So the check for the section size is okay. Now we can proceed for the next check. Now for minimum eccentricity check. So as per the IS 456 2000, L by 500 plus shorter dimension of the column divided by 30, we will get this value. Then L by 500 plus D by 30, so we'll get this value. And minimum eccentricity we have to consider as 20. So what code says that for every column you have to consider minimum eccentricity. For every column we have to consider minimum eccentricity. So here we are getting 12.47, 19.8. So if these values are less than minimum, at that time we have to consider minimum one. At least we have to consider minimum any time. In no any case you have to left the minimum eccentricity. So here we are going to consider as 20. Now another cross check is what? 0.5, 0.05D. So if this value 0.05D, see maximum of all these three value we have to compare with the 0.05D. So if this value 0.05D, your E minimum, if your E minimum is less than 0.05D, at that time you can design the column as axially loaded short column. At that time you can design this column as axially loaded short column. Otherwise you need to design this column as long with the eccentricity. You have to consider this column with the eccentricity. That's why this check is very important to make sure that your column is actually loaded or not. So just keep in mind, so this sheet will give the intimation that E minimum is less than 0.05 D. It means that design column as actually loaded short column. Now this sheet is applicable for this example. Next one is what? Slenderness check. Whether your column is short column, whether your column is long column, that we have to decide. That we have to decide all these things. Okay. So now slenderness check. Effective length divided by shorter transverse dimension of your column, effective length divided by longer dimension of your column, and both of these should be less than 12. At that time you can call it as short column. Otherwise this column will be long column and then you need to consider the additional movement. But L effective by B and L effective by depth both are less than 12. It means that your column is short column in both the direction. So this sheet will also give the intimation that short column about both the dimension, hence okay. Now finally we are going to proceed for the finding of how much percentage of reinforcement and how much area of reinforcement required for this column. So minimum criteria, first you have check how much minimum reinforcement is required. So minimum reinforcement is what? 0.8 times B into D. B into D is what? Minimum criteria. So 828 mm square is required as minimum reinforcement. Actual reinforcement, how much it is required based on the application of the loading. So 1236.72 mm square area of reinforcement required. So obviously minimum, your requirement is more than minimum. So you have to follow this reinforcement. You have to provide this reinforcement. Suppose after the calculation you are getting the area of reinforcement required, let's say 600 mm square only 600. So at that time sheet will follow the minimum one because minimum is more than the required. But in other situation, if your required is more than the minimum, then sheet will follow the maximum one. So overall is what a sheet will follow the reinforcement maximum of these two value. Now next thing is what we have to adjust the AST provided, area of reinforcement provided, by adjusting the numbers and diameter of bars. So here I am adjusting that. See, we have to check it provided AST is okay or not. Requirement is 236, so I would like to provide, yeah, 4 bars of 12 mm plus, okay, total bars of 8 bars of 12 mm. 8 number of, there will be no reinforcement on the another layer. So what, 8 bars of 12 mm dia. So provided reinforcement, how much it will become? That is 905 only. How much it is going to become? 905 only. No, it is not okay. Your provided is less than required. So again I am going to change it to, let's say, I would like to put it as 4 bars of 16 dia, 4 bars of 16 mm dia and 4 bars of 12 mm dia. How much it is going to become? 1257 and required is what? 1236. Now it's okay. Provided is more than your required. It's okay. Now percentage of reinforcement, how much percentage of reinforcement we have provided? So area, how to calculate the percentage of reinforcement, I hope you all know. So the provided percentage of reinforcement is 1.21. So it should be within the limit of 0.8 to 6%. So now it's okay. Next is what? How many number of bars are there along the depth of the column? Okay, let's say in plan view of the column, this kind of view of the column will be there in plan, that is 230 by 450. This is what? 230 by 450 is there. So 8 number of bars are there. 8 number of bars are there. So how I am going to put this number of bars? So 16 here. Always larger diameter of bars will be outer side. Remember, will be always on outer side, and smaller diameter of bar will be always in inner side. Okay, so this is outer of 16 and this is inner of 12. Okay, so along each face, how many number of bars are there? That is what? That is actually four number of bars are there. There are 4 number of bars. So we have to calculate the clear spacing between these two bars. We have to calculate the clear spacing between these two bars. So how we can calculate the clear spacing between these two bars? So total is what? 450. We are going to consider clear cover on both sides as 40. So minus 40, sorry, 40 plus 40, that is going to become 80, minus shear diameter. So shear reinforcement will also be there like this. Shear reinforcement, and the diameter of shear reinforcement I am going to consider as 8 mm. So 8 plus 8 from this side and this side, 8 plus 8 is going to become 16. This is done. Now diameter of bar. So 2 bars of 16 mm plus 2 bars of 12 mm minus 2 bar of 16 minus 2 bars of 12. So just calculate this value, how much we are getting. How much we are getting. So after calculating this value, 450, let me check it. 450 minus 80 minus 16 minus 16 times 2 minus 2 times 12. So I am getting the value as 298. 298. Now divide this value by the number of spacing 1, 2, 3. 3 spacings are there, 3. Just equal to, so 298 divided by 3. So I am getting 99.33. 99.33 value I am getting. So round up value we are going to take as 99. So spacing between these two bars, we are having as 99. So that's okay. As SP34 suggested that minimum spacing between the two bars, clear spacing, should be what? that should be at least 25. But practically, experts recommend that this spacing should be at least 30 to 40. So we are having 99. So that's okay, no problem. Your complete concrete will fill this space. So there will be no possibility of honeycombing, and proper compaction will also be there with the vibrator. Okay, so too close reinforcement is not accepted. So sheet will also tell you about this. So along each depth, along the depth or along each face, how many number of bars are going to be adjusted as per number. Sheet will calculate this by default. Now how much spacing is there? 99. Now it's okay. So always try to maintain this more than 30 or in between of 30 or more than 40 also. But it should not be less than, in any case, less than 25. Okay. Now design of this all done for the longitudinal reinforcement or for the main reinforcement. Now next is what we have to design for the lateral reinforcement, or we can say shear reinforcement. So diameter of bar that I am going to consider here as 8 mm. So whatever you want, any diameter of bar you can choose as per your requirement. Okay, so here I am going to consider 8 mm dia bar for the shear reinforcement. Now as per the IS 456 recommendation, three recommendations are there. What are those? Just try to understand. First one is what? The pitch. We have to consider least of the following. Least of following. What number one recommendation? Following. Number one recommendation is what? Least lateral dimension of your column. So 230 by 450 is there. So 230 is least lateral dimension. Second one is what? A 16 times smallest diameter of the bar. So 16 and 12 we have used. So here we are going to consider 12. So smallest diameter of bar 12. How much it will become? It is going to become 192 mm. And third one is what? In no any case your spacing should exceed 300 mm. So we have to consider least of all these three value. We have to consider what? Least of all these three value. So obviously least of all these three value is what? 192. That's why we are going to consider 192. But to round up the by rounding of the value, we are getting the final spacing or pitch of the shear reinforcement as 190 mm. So sheet will by default give this value, will automatically calculate this value. Okay, now next is what? Design summary. So sheet will also give you final design summary. So width of the column 230, depth of the column is 450, longitudinal reinforcement is 4 by 16, 4 bars of 16 mm dia plus 4 bars of 12 mm dia. So in combination we are going to provide the reinforcement. So outer is what? 16 and inner is what? 12. Total number of bars 1, 2, 3 and 4 in one line, second line, third line and fourth line. So along the one line, number of bars are, how many number of bars are there? 4 number of bars are there. Okay. Now next, lateral ties. So 8 mm dia at a spacing of 190 mm center to center we are going to provide for our column. So this is what total design and final design summary of your axially loaded short column design. Thank you.